Hello students, welcome to the video on the two-terminal structure of the field effect transistor module. So in the previous video, we have discussed what is meant by two-terminal MOS structure. So it consists of a metal, oxide and a semiconductor, and hence we will be having an inversion layer formed at the when we give n voltage to the gate terminal. So finally we have come to the conclusion that an inversion layer can be formed either if the material is a p type or n type. Now we will study the concept of mass capacitors in terms of its energy band diagram in this video. So coming to the energy band diagram, we have discussed already what is meant by an energy band diagram of a semiconductor. We know that the energy band diagram consists of an energy levels, different energy levels. So the EV is nothing but the energy of the valence band, and EC is nothing but the energy level of the conduction band. EF is the Fermi level, and also EFI is nothing but the intrinsic Fermi level. So the intrinsic Fermi level will be always at the middle of the energy gap. Energy gap is the gap between the EC and EV. And we know that for a p-type material, the Fermi level will be slightly nearer above, or it will be near to the valence band. And for the n-type material, the Fermi level will be below the conduction band. That is, it will be near to the EC. So now you take a mass capacitor, and the mass capacitor will be consisting of a gate, then an oxide or an insulator layer followed by the semiconductor material. So as an ideal case, that is when I am applying a zero voltage across the mass device or across the gate terminal, there will be a thermal equilibrium state, and hence the energy band are flat. That is, it indicates that there will be no charge in the semiconductor. So this condition is called as the flat band. So we assume that when VGS is equal to when gate is equal to zero, when gate voltage is equal to zero, so the system is in the thermal equilibrium, and hence there is no charge carriers, and the energy band will be a straight line if throughout the semiconductor material. Now you assume that I apply a voltage such that a negative voltage is applied to the gate terminal, and the semiconductor is a p type. Now when I apply a negative bias, the valence band edge is closer to the Fermi level at the oxide semiconductor interface than in the bulk material. That is, we can see in the diagram that there is a when there is a change in the curve at the surface at the surface at the surface, or I can say that near the interface of oxide and the p-type material. So the energy level increases. It indicates that it appears to be more p-type than the bulk material. So the Fermi level is constant in the semiconductor because in the mass system the semiconductor is in the thermal equilibrium, and hence there is no current through the oxide, or there is no movement of charge through the oxide. And the next case is when a positive voltage is applied. So when a positive voltage is applied to the gate, we can see that the conduction and the valence band edges bend down, indicating a space charge region similar to that of in a PN junction. So we have seen in a PN junction diode, that is when it is forward by reverse biased. So and in a p-type material, there will be still a decrease in the energy level of the holes. That is, if more electrons are there, we know that the energy level will be increasing in the it will be increasing, and hence because here the depletion of the charge carriers will result in the bending of the curve. So the conduction band and the intrinsic Fermi level move closer to the Fermi level. The intrinsic Fermi level both move closer to the Fermi level. So this indicates that there is a space charge region. We assume that the space charge region width is xd. Now we take a large positive voltage is applied to the gate. Now what happens is the intrinsic Fermi level at the surface is now below the Fermi level. That is, my Fermi level is can be seen closer to the conduction band, or the conduction band at the surface is now close to the Fermi level, whereas the valence band is close to the Fermi level in the bulk semiconductor. So this result implies that the surface in the semiconductor adjacent to the oxide semiconductor interface is N-type. That is, we have created an inversion layer of electrons at the oxide semiconductor interface. The energy band of the mass capacitor here, it is for the large positive voltage gate bias. So when I apply a large positive voltage for a mass capacitor with a p-type semiconductor, then an inversion layer of electrons will be formed at the surface that is adjacent to the oxide semiconductor interface. Now, this indicates the formation of inversion layer. Similarly, when I take an N-type substrate, applying a positive voltage will result in the formation of accumulation of electrons. So, the more number of electrons, so the region becomes N plus. Whereas when I apply a negative voltage, it will result in the formation of the space charge region initially, and then if still more negative voltage is applied, then it may result in the induced positive charge, positive holes at the interface or at the junction of the oxide and semiconductor, and it is called as the inversion layer. So applying a proper bias to the gate terminal will result in the formation of the inversion layer in the N-type as well as the P-type semiconductor of the mass capacitor. So for the N-type semiconductor, we can see that when I apply a small positive voltage, so here we can see that the Fermi level will be nearer to the conduction band for the N-type semiconductor, whereas when I apply a positive voltage, the EC, that is the conducting and energy band, will be bending down. Now, due to the applied positive voltage, there will be a reverse in the energy band diagram. That is, the curve will, the energy band, which is flat for zero voltage, will now bend upwards, indicating the formation of the space charge region. So, in introducing a large positive voltage to the gate bias, will still increase the bending of the energy band, and because of that, we can see that the valence band will be close to that of the Fermi level, and hence because of that we can say that this region, which is near to the interface of the oxide and semiconductor, will be converted it will be converted to the positively charged holes accumulation, or I can say that the n-type region we have formed a layer of holes which is called as an inversion layer. So in this video we have discussed about what is mass capacitor of both n-type and p-type, and also we have studied how the energy band diagram works, or how the energy band diagram can be used to explain the formation of inversion layer. Thank you.